let's go over what you have, guys. This is really important that you catch these parts, how to do these continuities. And Will, I think you were the only one not here yesterday. Anybody else not here?
Raven.
Oh, Michael? Michael wasn't here. And Raven, you were here for a little bit, right? 2 minutes. Okay. All right, so the first thing we're going to do is do this test. This test, and that's all they wanted you to do in the first part too. You need to make sure, this test makes sure that this approximates a normal curve. We looked at four-wheeler graphs in chapter 5.5, and when both of them were greater than or equal to 5, your curve was actually looking like a normal curve. This will never say normally distributed, and it will never be n is greater than or equal to 30. Instead, this is the test we do. So if it passes the test, then we can say the mean is n times p, which you already did here. And then you can say the standard deviation is the square root of n times p times q. So you would take your n times p and multiply it by your q, and then take the square root of it. If you pass the test. If you fail the test, either one of them fails, always go, we said yesterday, go for the smaller one. If the smaller one fails, doesn't matter what the larger one does. So, and if the smaller one passes, then the larger one has to pass. So just stop there, we can't do anything else. Okay, then you had to match. These are corrections for continuity. So for you guys that weren't here yesterday, for instance, from this, we say if x is greater than 109, what's the first number that I'm going to count? Well, I have to say greater than 109. Well, not yet. Give me a whole number. 110. Then 111. Blah, 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 blah. All the way up, right? Our rule is you take the lower one, you drop it 0.5 down. So this will become 109.5. You take the higher one, you bring it 0.5 up. We don't have a higher one in this case. We just have a lower one. So then we just rewrite the statement to say this. What happens is, in a binomial distribution, everything is whole numbers, integers, positives. But everything is whole numbers. So when you're making your curve, if you had a bar for 4, because it's only 1, it would just have a single line. 4 and 5 would just be a single line. You need to make this a continuous bar graph because you're working on a curve with a continuous number line. So what we want to do is expand this bar to go halfway. So when you meet somebody halfway, this guy will drop a half down, this one will raise a half up. So when we write our probability statement, we take a look at where our data starts. The lower one drops 0.5, the higher one raises 0.5. So in a case like this, we said it's greater than or equal to 109. We start with 109, 110, blah, blah, blah. We drop this guy down to 108.5. Will we ever find 108.5 in a binomial situation? No. So the first number we will hit is 109. Now, yesterday we talked about it doesn't make sense yet until today when we put the probabilities in there. And the only difference is we'll use this number in your z-score versus 109. It just makes that area cover a little bit more. Because you had to take your continuous number line and put your discrete values on there and make them expand to fit, which will cover slightly a little bit more area, if you think about it. Now here's the lower end. X is less than or equal to 109. So this says 107, 108, stop at 109. This is my upper end. My upper end raises 0.5. Now, if you want to keep your equal sign in there, if it's the same, that's fine. The equal sign does not matter when you hit these because you'll never hit a 0.5. But if you know, some kids like to keep the original statement if it said less than or equal to, they put less than or equal to. And I'm fine with that. This guy says you're less than 109, so you're 107, you're 108, and you don't use 109. Raise that guy up 0.5. Today we're going to see why we do that. Because when we do your probability, it just gives that a little bit more area. Because we extend that bar. Not a whole heck of a lot more, because you're only going out half. But we do extend it. You good with that? You guys that were in here?
Yeah.
Okay. Good. We'll work more with it today. And this one, they just took the opposite approach. They wanted you to put this in words the way you read it, and then correct it for continuity. So this is the probability that something is less than 25. Sometimes they say fewer than 25. And therefore, there would go dot, 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 23, 24, less than 25. Take the last one, raise it up. Try for these not to say greater than or equal to, because usually in our sentences we say at most, at least. This is more of the at least type. If you said greater than or equal to, that's fine, but that's usually not how we say. We usually don't ask the other person, do you have greater than or equal to $10 in your pocket? We usually say, do you have at least $10 in your pocket? We don't say, do you have greater than or equal to $10? They would say, what a math nerd. So, we usually say at least, at most. And again, if you're starting at 110 and you're going up, drop this guy, 0.5. It kind of makes sense. You're just bringing it out halfway to meet the other person. The probability of getting exactly 33. Exactly 33 is different. Exactly 33 says, here's my graph. This time my x's are down here, so I can show you the number line. Usually we see them up here. This is 33. It doesn't have a bar. It has just a little line. To give it a bar, we have to go half this way. We have to go half this way. So this is 32.5 to 33.5. It actually ends up like an in-between. So when we do an exactly with the probability, we're going to see it today, you have to actually do an in-between. You have to expand both sides of it. It's its lower and it's its upper end. Kind of a weird concept, but if you kind of think about it, if you need to make a bar out of this whole thing, you need to expand both sides of it, because it sits all by itself. Greater than, if you said the probability of greater than 65, or you say more than, that's fine. So you're at 66, 67, you can't use 65, drop this one down. And you won't use 65, and you won't use 65.5. The first one you'll hit is, in fact, 66. Probability of getting, again, less than or equal to, we don't really ask, do you have less than or equal to? We say, do you have at most? So if you want to use the at most words, usually what they do is they give you this, they have you write the statement. They just ask it to you backwards to see if you're interpreting it the same way. And again, here's an in-between. Here's an in-between 55 and 60. Now notice they didn't include 55 or 60. We talked about this yesterday too. We used the word inclusive. Inclusive, if I included them, it would have an equal sign. And I would say 55, 56, 57, 58, 59, 60. I would jump this one up, I would take this one down for inclusive. Because this does not include them, it's really 56, 57, 58, 59. Question?
So, like, how do you know when to go up or down?
Your lower level, your lower end, is always dropping down. So your 56 here has to bring a half of one back behind it. Your upper one, 59, has to bring a half of one up. So your lower end is going to drop 0.5. Your upper end is going to raise 0.5. The thing is, you have to determine what is that number. So whenever we see these probabilities, we write them out. This one's always tricky, because if I say between these two numbers, I don't count those two numbers. So I'm really looking for 56, 57, 58, 59. I drop this guy down 0.5. So 55.5. I raise this one up 0.5. 59.5. If I included them with an equal sign, then I drop this one down 0.5. I drop this one up 0.5. The inclusive one is tougher. Like if you think of the numbers 1, 2, 3, 4, 5, and I said What are the numbers between 1 and 4? What numbers are between 1 and 4? 2 and 3. What numbers are between 1 and 4 inclusive? 1, 2, 3, 4. That's the difference between the less than, a less than, and equal to. So if we write them out, we can see them a little bit better. And in the beginning, write them out. I still write them out. If you make a mistake there, then your area is wrong. And this one just said, 18 just said, can you use the binomial distribution and will it approximate a normal distribution? That's what your test is telling us. Your test says, does this binomial distribution, remember we did binomial success and failures? Like 85% chance of the operation being successful. I did 7 patients. What's the probability that 4 of the 7 are successful? That's your binomial. Does this binomial distribution approximate a normal distribution? If it does not, then we cannot use your z-score. So if it does, then we can use your z-score. That's what we're about to do today. Use the z-score with it. But if it fails, we stop. And another way we recognize these, if you take a look at this, the next problem here, we're going to be doing this today. If you survey 67%, they respond favorably, and you ask a certain amount of people, if you go to make your z-score, you have no mean, you have no standard deviation. The only thing that's going to get you a mean and a standard deviation are these formulas. The only thing that's going to allow you to use those is testing your NUP and your Q. So you're going to see it's pretty easy to spot once we get there. If it passes the test, then this automatically is your mean, because this was n times p, and then n times p times q, square root, is your standard deviation. Then you'll be able to use your regular z-score formula, which we're going to do now. So does this make sense? This one passed the test. You take n, times it by p, then you take n, times it by q. It has to be greater than or equal to 5. If it is, then you say it's a go. Yep. It says, amongst everything else, amongst being what we're looking for, it has to have 2 choices, a success and a failure. It has to happen n amount of times. The probabilities don't change, and the x variable goes from 0 to whatever we're going to. It applies to all of them. It doesn't even have to start at 0. So verify that it does. Once you found your NUP or Q, make sure you do your test. If it fails, stop there. If it fails, you stop. You don't do anything else, because then it does not approximate a normal curve, and you cannot use your z-score formula. If it passes the test, calculate your mean and your standard deviation. Apply the correction for continuity to your probability statement, and then today we're going to find your z-score. As we normally do. Is it to the left, is it to the right? We do the same thing. Our only big difference is we have a 0.5 out there for your x value. Everything else will work the same. So let's take a look at one. It says, in a survey of 8 to 18-year-old heavy metal users, and we were asked before, did this work? This was from your other example, and we checked this already. We said yes, this is binomial, success 0.47, failure 1 minus that. We said we randomly selected 45 people. Okay, and we want to know what is the probability that fewer than 20 responded yes. How do I write that probability? Good, x is less than 20. Now, first thing we do is n times p greater than or equal to 5, n times q greater than or equal to 5. Our n is 4 to 5, our p is 0.47. Now, if you right away try to use a z-score, you have no mean. You have no standard deviation. So that's how you identify this. You say, well, how am I going to get a mean and a standard deviation? It's got to be by those two little formulas. And your n, 45 times 0.53, greater than or equal to 5. So they both pass, right? So your mean is this guy. And your mean happens to be 21.15. We did this, but now we're going to continue with it. And what's your standard deviation? What is their standard deviation here? Your standard deviation. Help me out. What does your book say? Three, 4, 8 or 3, 4, 7?
3.348.
8. Okay, thanks. Now.
No, 3.3.
3.3.
3.348.
So make it 3, 5. So make it 3, 5. Is that good? All right. So now we have a mean and we have a standard deviation. Now we can use your z-score formula. But before we do that, we just have to correct this for continuity. So if it's less than 20, I'm coming along, I get to 15, 16, 17, 18, 19. Do I count 20?
No.
No. So I take my upper one and it goes to 19.5. So my new probability statement says this. X is less than 19.5. This is the one that I use for my z-score formula. There's no central limit theorem here. We're back to your z-score formula. So you're going to use your x of 19.5 minus your mean that you just found over your new standard deviation. And then you're going to find your z-score. So your z-score should come out to be negative 0.19. Everything else is the same. I want my area to which way? To the left or to the right? I'm pointing that way. I want my area to the left. I look this up in my table, look it up in your calculator, get your area to the left, and it's 3121. So I have the probability that from this group of 45 people in this age group, if I ask them if they had 4 grades, the probability of them saying yes is about 31%. About 31% of them are going to say yes. So we have a couple of things. We first did, is this binomial? We looked at all our n's and p's and q's. We did a test. It passed the test. We're good. We found the mean and the standard deviation. We corrected for continuity. Then we did a z-score. So we have a couple of steps extra in here. Correction for continuity is one of them. Testing to see and finding the mean.
So it doesn't pass the test.
We stop. We say this binomial distribution does not approximate a normal distribution. So you can't use it. Now, most of the time, when they give you a problem in the book, it's probably going to be able to use it. Otherwise, it's kind of a wasted problem. Okay, don't pack it up, guys. Try yourself number 3. Come on.